Okay, so how to assign oxidation numbers. So there are a series of like rules for assigning an oxidation number. We need to change this pen from red. So an oxidation is a number that is given to each atom based on electron assignments. I would also say arrangements. Please do not judge my spelling. It's early in the morning, and I'm not an English teacher. Good? If you're looking in your textbook that we use in class for TRO, we use the TRO. This is the rules for assigning oxidation numbers is page 177. Okay. First one is the oxidation state of an atom in a free element. So like our diatomics, Hofbrinkel, do you guys remember those? Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. They all come in pairs, and that's how they exist as an element. Those, as well as any atom that is existing on its own without a charge in its elemental state, those all have an oxidation state of 0. Okay, because they haven't changed how their electrons are being shared from their normal free state. That makes sense? Then 2 is monatomic ion charges are equal to their oxidation state. So if it's an ion that's existing on its own, so the book gives like chlorine, the oxidation state of chloride ion is its charge, -1. Okay. Then the sum of oxidation states of all atoms in a neutral molecule or formula unit is 0 or equal to the charge of the ion. So it gives like H2O, right? All of these oxidation numbers are going to be equal to 0. Correct? That makes sense. That should jive. And then same for like nitrate. All of these oxidation states will add to the -1 charge. In their compounds, metals have positive oxidation states, just like in so ionic compounds. There we go. Ionic compounds, if it's written as a compound, their charge is their oxidation state. It's very much tied to this. So if I have sodium chloride, chlorine forms a 1- charge, so its oxidation state is -1. Sodium forms the +1 charge, so its oxidation state is +1. 5. Compounds. Nonmetals are assigned oxidation states according to a table that's given. And there are a few exceptions, so that's why I wrote this down, so if you wanted to review later. In general, you assign it according to their electronegativity and try to stick as close to any pretend charge that they might have, especially if they're metals, like their actual ionic charge, versus like when we get into this, you'll see nitrate. Nitrogen will have a very different oxidation number than its normal charge that it would form for nitride. Okay, because that's a 3-, but nitrate we'll see is a very different oxidation number because it's covalently bonding. So there's a few rules to go with that, and they are summarized in your notes as well as on page 177. Okay, do I need to write those down again for you, the rules?
example of how to like
I have examples, but do I need to write down the rules?
these ones right here?
Uh-huh.
Well, now they're in.
They're in your notes. Okay. Do you have your notes out? Yeah. Might want to pull out your notes. Okay, here we go. Assign an oxidation state to each atom. I'm going off of practice problems in the textbook. So for our first practice problem, we're going to assign the oxidation number for chromium, elemental. Okay, so what would the oxidation number be for Cr? 0. Why would you say that? Its charge is 0. It is existing in its elemental state or its free state, so it has no change in its electron assignments. So it would be 0. Now looking at B, what is the oxidation number for the chromium 3 ion? Positive or negative? Positive 3. Notice we have to assign a sign for it, positive or negative, and then the number. How did we get the positive 3? The charge on the ions. So ions take, like monatomic ions, take their charge as their oxidation state. Okay, for all elements in carbon tetrachloride. So we have carbon and we have chlorine. Going back to our rules, if we read them, oxidation state of any element given generally depends on what the elements are, groups in the compound. Rule, No. So fluorine gets a -1, hydrogen gets a +1, oxygen gets a -2. These are all in order. Those are not in here. So my next one is group 7A gets their typical group charge as their oxidation state. Do we have something in group 7A in there? Might want to actually use your periodic tables. Chlorine, right? Chlorine is in group 7A. What charge does it typically form? -1, so that means its oxidation state in this is going to be equal to -1. To find carbon then, since we only have 2 in here, we would use a little bit of algebra. So carbon plus 4 chlorines has to equal the overall charge on the compound, which is 0. Does that make sense so far? Okay. Solving for this, what is the oxidation state of carbon equal to? Say it loud, say it proud. +4. Okay. Cool. Questions? Concerns? Okay, D. These are the practice problems from page 178, if anybody's in your textbook. Strontium bromide. Okay, what type of compound is this? Is it molecular or ionic? Ionic, so easy for this one. Its oxidation numbers come from its charges. So what's the charge on strontium? What's the charge on bromine? Yep.
But if there's 2 bromines, would you do -2?
Mm-mm. It's each individual atom, right? Because when we then look at this, +2 plus 2 -1s, that does add to the 0, which is the overall charge on the compound, right? So they should cancel out. We have the 2 here is used for charge balance or your ratio. So that way the charges of the 2 sum to 0, right?
Supposed to be 0.
Yeah, for ionic compound, like your compounds, molecular compounds, ionic compounds, they should be 0. If they are not, we call those polyatomic ions. Cool. Okay. And a hint, whether or not it should have a charge, it won't have one here if it doesn't have one, if it's 0. sulfur trioxide. Here we go. So, molecular compound, right? So we have to work down our rules of what we assign. It's not fluorine, which is a -1. It's not hydrogen, which is a +1. It does have oxygen, which is a -2. So oxygen gets the -2. Sulfur gets what? 6. Okay. Sulfur plus 3 oxygens has to equal, what's the overall charge on this compound? What's the overall charge? 0. Thank you. Okay, so using some algebra, we get that it must be what, Kayla? Can you see it down there? Are you awake?
Yeah, I'm awake. I think. So I have to equal it.
Yes. All right, solving sulfur minus 6 is 0. So sulfur must equal +6 for the whole thing to add to 0. Cool. Sound good? So why do we use oxidation states? It's a way for us to show how electrons are being rearranged or redistributed as things change their bonds. It's just a system for trying to organize that information and see how that might shift. Okay? It allows us to then identify the reduction and oxidation halves of a redox reaction.
So that's what
Yep,
that's the 4.9.
that's 4.9. So they will specifically ask you, hey, what type of, is this a redox? Or identify the oxidation and reduction, like what's being oxidized and what's being reduced in a reaction. And usually when it asks you that, the first thing you need to do to be able to determine if something's being oxidized or reduced is assign oxidation numbers, right? Because based off of changes in the oxidation number, you can determine, is this being oxidized or reduced? And we'll get to that. Ready? Okay. So, using oxidation numbers, we're going to determine if something is being oxidized or reduced, like what's being oxidized or reduced in the reaction. And I don't like those. Those suck too. Hold on. Well, I guess we're just going to go with it. Here we go. Going back. Okay. So, a practice problem from the textbook. I'm just going to use that. That one works. Checking real quick that it's balanced. Well, it gives you a coefficient. It's probably balanced, right? But you can also check for hydrogens. Whoops. 2 and 2 is 4 hydrogens, 2 oxygen, magnesium. So it is balanced. Okay, so we're going to determine what is being oxidized, what is being reduced. So if we're being asked to determine oxidation and reduction, our first step is to assign oxidation numbers. Good there? So why did we learn how to assign oxidation numbers? So we can analyze a reaction. So start by assigning them. So magnesium, this first one, what would be its oxidation number? 0, because it's elemental and by itself. Moving, what's up? Sorry.
I think my problem is I don't know when to use the charge and when to just call it 0.
Is this bonding to anything? 0. Does it have a charge on it? No. 0. That help? Okay. Next. Water. Is stuff bonding to things, not itself? Yes. Right? It's bonding to, like, hydrogen is bonding to oxygen, right? So it's not a diatomic element. Electrons are being changed from how they would normally be distributed. So it has non-zero oxidation numbers. That was a good question to ask. Thank you, Lyric. So starting here, the order addressed in the textbook was assign fluorine, then assign hydrogen. Is hydrogen up there? Yeah, so what does hydrogen typically get? +1. Let's start by making sure we put the sign. So like you telling me 1, we need to say +1 and think +1. Or 1 plus. There's a difference between the two, but it doesn't matter for any sort of chemistry you'll take until you get to your graduate degree. Cool. Okay. So then if this is +1, 2 positive ones plus oxygen has to add to what? 0. So what does oxygen have to be? -2. Good there? That makes sense? Okay. Well, I'm showing all of the work. You'll get faster as you practice. So I know what you guys are doing in the next 2 days is practicing. Okay. So here, magnesium hydroxide. This is a polyatomic, and we'll come back to it in a second. But this whole compound, is this molecular or ionic? I just told you this was a what? What? Ion, so it is ionic. Then that means that magnesium's oxidation number is its charge. So what is the charge on magnesium? So it is a +2 oxidation state. Good. So then hydroxide, OH, is a polyatomic ion. But what is the overall polyatomic ion's charge? Polyatomic ion. If this is 1 +2 charge, and we have 2 somethings, they have to add to 0. Well, this has to be -1. This whole thing has to be -1. Yeah, because there's a 2 on the outside. So we know that this whole thing is -1. So OH has a -1 charge. So oxygen plus hydrogen has to equal -1. So hydrogen we know is a +1. Oxygen is what? 2 to give us -1. So those don't really change. And you'll see that happens, is that they don't change. Sometimes. Like you'll have one specific area where they do change. And then our last one over here. What is the oxidation state on this, Sam? You don't get to say. Oxygen is -2. Hydrogen is +1. That better? Thank you. Now for hydrogen gas. Is it? 0, I told you you couldn't say. Why is it 0, Sam? It has no charge and it's by itself, right? It's a diatomic element. So that's how it exists naturally in its free state. It's got a buddy. Okay, Siamese twins of the elemental world. So it is 0. 4-9? No, you didn't have to do that. 2. Good? Good on the assign. So when we need to determine which is being oxidized and which is being reduced, first we assign the oxidation number, then we identify, so identify, ID, changes in ox number. And these are always based off of the element. So we look on the left, we look on the right, where do we see the charge, the oxidation numbers or our pretend charges changing? What's the first one you see changing, the element changing? Magnesium. So there's one. Oop, I can't draw a straight line. Where's the other one changing? If one changes, there's always a pair. Hydrogen, right? So it has to be this hydrogen, and it doesn't matter which one over here, one of them is going to switch. Oh, or two of them, I guess, technically. So there are our two half reactions. Okay? One of those is an oxidation half, one of those is a reduction half. Our third is to remember that Leo says gur. Good there?
Can you say that, like what it is?
Lose electrons, oxidation. Gain electrons, reduction. Alternatively, you can use oil rig. Oxidation is loss, reduction is gain. That makes sense? So either one works. So which set, magnesium or hydrogen, are we losing electrons? Well, we have magnesium, going from 0 to +2, and hydrogen going from +1 to 0. What charge does an electron have?
Oh, so when you're like adding the +2 electrons.
Yeah, so remember, losing an electron, right, is positive. Gaining an electron is negative. So when we say a loss, we're actually saying it becomes more positive, right? Because you're losing negative. So which one's becoming more positive? Magnesium. So this is my oxidation. I-O-N. Oxidation. And so then this one is my reduction. And they'll always be paired that way. You'll have one that is being oxidized, one that is being reduced. If you get to inorganic chemistry eventually, they might torment you and couple more reactions together, but no complicated, well, this is complicated enough. They aren't going to torment you beyond that. Better? Okay, what's confusing that we need to clarify before we move on?
Is that the last step?
Yeah. Yep.
Are you going to go through like how to do the reaction or no?
The half reactions? Yeah. Yeah. We can tie like how to balance half reactions into this and do a little more review before we do half reactions.
That's what I'm confused on. It's like eventually. What I'm confused on is when you get like I can get to the half reactions and I can add like the H2O and the H and the electrons, but I get confused whenever
You have to recombine them
no
or identifying which two.
like no, it's whenever like on one of them, the one you did with us the other day, the like number 1, you multiplied the whole side by 3.
Oh, it's so your electrons cancel. So we'll go over that, but like you have to make the electrons in both half reactions the same quantity. So when you add them back to each other, you don't have free electrons roaming around. Because in redox reactions, one atom loses electrons, and all of those electrons are gained by another. So for them to be stoichiometrically balanced, big word for the day, and I said it correctly, hey, for those to be stoichiometrically balanced, the electrons have to be equal in quantity on both sides, because what's lost by one has to be gained by the other half. And so they must be equal, so we multiply by a coefficient to a whole reaction so it stays balanced, but now its ratio works with the other half. Does that make sense? A little bit? Shall we see it in application? Okay. I went through and I bookmarked because somebody in third period decided to be helpful and actually ask questions ahead of time. Okay. And I'm actually using textbook. That's why I posted the discussion board, because I can go ahead of time and organize it a little bit better. But it's fine. We'll make it work. Here we go. Balance the readout. And I can actually find, like, if it's well enough in advance, I can find, like, real questions from maybe an AP test. But I didn't have enough time because none of you asked before class. So here we go. Balance the redox reaction in acidic solution. Let's go with we'll do the easy one first, I guess. H. That's just too easy. No. Copper. Yes, it is. Well, these are both easier than what I put in your worksheet. My bad.
I did it, and for the first half, I got +2 electrons on the products and +2 electrons on the reactants. And then on the second, half of the reaction, over here, I got +2 electrons on the products. And then I was like, well, how do I cancel all 3 of those out? Because I know
you added in the first half electrons to both sides?
Yeah.
No, one side. One side. Because both sides, if they should not be equal in charge, so you only add it to one side to make the more positive side more negative. But we can talk about that in a minute. I can look at your stuff too.
Technically 3, but it's because I did 4 before I did 3. I got it. I can't even get past 2. I'm like really.
Okay, ready? Ready? Reteaching. So we have to identify the half reactions. You're going to look for commonalities. So I see I have a copper and a copper here. And so there's one half reaction. I have a nitrogen and a nitrogen. I will usually not use oxygen or hydrogen as common factors for developing or identifying a half reaction because oxygen and hydrogen are everywhere. Okay? In question 1, we only used, I think it was the hydrogen, or was it oxygen?
It was a hydrogen.
The hydrogen in question 1 from the 4-9 worksheet as a half reaction after we had gotten the other half, right? I'm like, oh, this is all that's left over. It must be the other half reaction, right? I have other things to identify that half reaction. So this is my other half, and that was written really poorly. Okay? So I'm going to write my 2 halves separately and balance them separately. Okay, so we can do them simultaneously, I guess. Our first step is to balance all atoms except oxygen and hydrogen first, using coefficients. In the copper half reaction, do I need to balance them? No, I have one of each. In the nitrogen half reaction, do I need to balance nitrogen? No, I have one of each. So I'm going to leave that. Now, we go to our next step and we balance oxygen by adding what? Water. Yes, exactly. So I don't have any oxygen in this, so I skip it. I go over to this side. I need water because I have 3 to 2. Which side am I adding water to? Product side. Good. So how many? Okay. So after adding water and balancing oxygen, I now balance hydrogen by adding what? H+. Okay, it's acidic medium, so we add acid. The ion that we use for shorthand notation for acid is H+. So which side am I adding? There's no hydrogen here, so I skip it. I have hydrogen here, so what side am I adding hydrogen to? The reactant side. How am I adding it? H plus with a 2 coefficient. Good?
Yeah.
Why do I have to add this? Because to balance oxygen, free-floating oxygen as oxide is insoluble generally. An oxygen atom free-floating is a free radical and is going to be highly reactive and bust up your reaction. Not great. Usually in redox reactions, the oxygen is coming from or going to water when it's reacting, because these are all aqueous solutions that are reacting. So it must be water that we use to balance oxygen. Okay.
So for every time that we do,
You balance. Oh, I need to balance my oxygen. I add water. Yeah. Okay. Cool. Okay. Next. So after adding water, it messes up the balance because now I've got a new atom in there. I need to add some protons or hydrogen ions. Bless you. Okay. My next step is to balance charge. So I balance atoms, I balance oxygen, I balance hydrogen, now I balance charge. Okay. So I need to make both sides of each half reaction equal in charge. Looking here, I have 0 and +2. I balance charges with what? Electrons. So which side am I going to add electrons to make these equal?
no
Products. Remember that electrons are negatively charged, so we add it to the more positive side. Okay, so adding how many electrons? 2, oops, 2 -1 charges, so I'm going to add 2 electrons here so that this becomes 0. Good there? I'm going to put a little divider. No, I don't know why my laptop's running slow. It probably needs an update. Next, I'm going to do my right-hand half reaction. Figuring out the total charge on the reactants. What's the total charge on this side? Positive or negative? +1. 2 positives plus a negative is a positive, maybe 1. And then I need to make that equal to, what's the total charge on the product side? 0. So how many electrons do I need? 1. On which side? So I'm going to add an electron there, +1 electron. And so that means I'm adding a -1, and that makes that 0. Good so far? Before I can recombine them, I need to make sure that my electrons are equal in quantity so that they cancel. Yes. So this is where I do the parentheses and multiply by 2, right? Because I have 2 electrons here and 1 here. The easiest way to make those equal is to multiply all of this by 2. Cool? I multiply the whole thing by 2 so I don't disrupt the balancing I had already done. So it still is balanced because I'm going to multiply it all by 2. But now I have the same number of electrons in my right-hand reaction as I do in my left-hand reaction, so that what is made is used up perfectly. Okay, so writing it out, I have 2 electrons plus 4 hydrogen ions, and there's a delay, plus 2 nitrate ions, and I'm going to be horrible and skip my states of matter. Yields 2 nitrogen dioxide gas molecules plus 2 waters. I also am lame and... Wait, did she disappear? Okay, good so far? Okay, so we multiply everything by 2. I'm going to bring my other half reaction down, and I like to line my arrows up. I might like to line my arrows up. There we go. I think my computer is struggling this morning. We're going to restart this baby. So copper solid yields copper ion and 2 electrons. So notice what electrons I lose are gained by the other half reaction. Does that make sense? And I don't have leftovers.
Does it have to be on opposite?
And it must be on opposite sides, okay? Because notice, these are losing electrons. So this is the bottom one is my oxidation half reaction. The top one is my reduction because it's gaining. Cool. So it's redox because you always have one half that's being oxidized, one half that's being reduced, and they're coupled. They are paired. Okay. We'll look at it in more application when we get to Unit 9. What's up, sweetie?
How do you know which one's losing and which one's gaining? Just because like it's on the product side of the reaction.
Yep, product side, right? So this copper lost the electrons. Or when we go back to our oxidation states, this was 0 and this is positive 2. 0 to a positive 2 is a loss of electrons, oxidation.
Wait, so copper lost the electrons?
Mm-hmm. Right? Yanked them off, became an ion. Right? Going from a 0 charge to a positive 2 charge, what do you do to the atom?
Take them away.
We need coffee in 5th period. And then the top one, we add those electrons, right? And it's actually the nitrogen that's gaining those because it's going from a +5 oxidation state to a +4 oxidation state. So it gains the electrons. Everything good? Trash cans?
No. Who's blowing a whistle? It's driving me nuts. I think it's somebody in my study hall, but they're all looking at me like I'm crazy. Somebody's out here going over and over.
Are you sure it's not the dump truck backing up? Oh.
It's like a whistle, like a sports whistle.
I am so gonna have to re-record this video.
No, we should keep it in the video.
Keep it in the video and you guys just either enjoy the break or fast forward. Okay. Unedited, always, guys. Miss Bernie got time for that. Normally, beyond just canceling out the 2 electrons, you cancel out what's the same on both sides of each half reaction, right? And simplify. This one is actually an easier one. And this is actually closer to what you might see on an AP test. So that's it. So we're going to add them together. Oops.
What in the world?
So would it be easier to determine the oxidation or reduction when you're doing the charges at the beginning?
Like doing this 0 + 5 - 2
No,
plus
the
2.
0 equals +2 plus.
So I'm not doing all of the oxidation numbers as I do this. So you mean when I'm balancing the charges on both sides of so the oxidation number is kind of like a pretend charge based off of electrons being changed due to bonding, right? Because a real charge is only for ionic compounds. That's why an oxidation number, if it's an ionic compound, the ions charge, as long as it's monatomic, and the oxidation number are equal. That makes sense there? Okay, but nitrate or nitrogen dioxide are molecular compounds. So they don't really have charges, but we assign them oxidation states anyways because their bonding is different than they would be in their elemental state. Sorry, I'm having a hard time putting the words together. An alternate method for identifying your half reactions is to assign the oxidation numbers and look for what changes. Right? Because we assign the oxidation numbers and we can do our next example that way. And we look for what changes. Copper changes, nitrogen changes. Oxygen does not. So oxygen is not a half reaction focus. Nitrogen is. So I continue writing out my entire half reaction. Or not half reaction. Now this is just it. And mine is like lagging too, so I'm like trying to write it and hoping I'm not writing over other stuff. So if it looks funky, ask me. This is our balanced half reaction in acidic media. Cool?
Yeah. I said so. If you had like 6 H2O, like at the top on the reactants, and like 4 H2O on the
Simplify.
bottom,
You cancel out the 4 and
make it 2 H2O.
yep. Cool. We have time. Do we want to do another one?
Can we do one from the worksheet?
Yeah.
Number
3.
Yeah.
Oh my god, Miss Bird, I did number 3.
We should just cancel it.
Wait, what's the difference in the other ones?
Once it's
So for basic, after you add the H plus ion, you add OH to cancel them out, and we'll do a basic media because somebody asked. I don't think it was this class, but somebody asked. Time permitting, we'll do basic media or medium. So you have to always add the acid to balance your protons, but because you're in basic solution, you add hydroxide ions to both sides to cancel out your acid. So then it's now basic. But when you cancel out your acid, hydrogen ion plus a hydroxide ion makes what? Makes what? H plus OH minus makes what? What's the product in all titration reactions? Oh, that one's fun. In the 4.9 worksheet. Here we go. Rhenium ion of some persuasion. Practicing. Let's practice. We're going to assign our oxidation numbers. So looking at these, going through it, what's the easiest oxidation number to assign? Out of all 4? RE, what is it? 0. Woo! Okay, now the rest. Okay, now think about it. What's the next easiest to assign? No, atom. So IO, that's a capital O. So what's the next easiest atom to assign? No, that's... No. So we have RE, we have oxygen, and we have iodine. Okay. What is the next one that is probably easiest to assign because it's probably not changing? Oxygen. So -2 for all the oxygens. Okay. Because you go through your list of stuff, you assign all the elementals, then you assign fluorine, -1, then you assign hydrogen, or you assign all your ions then, I guess, but we don't have any like monatomic ions. So then we do fluorine, then we do hydrogen, none of those are there. Then we do oxygen as -2. Cool?
What was fluorine?
1. Fluorine is -1. Hydrogen, +1. Because that's the charge it tends to form. Okay. Okay, now we can assign the rest. So we know that RE is equal to 4 times, or RE plus 4 times -2 is equal to -1.
Oh, that's an 8. I was
I already know it's equal to -1.
overall charge on the polyatomic ion. So all of the oxidation numbers always have to add to the charge on the overall compound or polyatomic ion. Compound, it is 0. Polyatomic ion, it has an overall charge. Good there? So practicing with the next one. IO, so iodate, iodus, hypoiodite. I think that's the name of it. Anyways, the IO ion. What does it have to be? +1. Do you get that?
No.
Okay.
Where did that even come from?
So iodine plus oxygen has to equal the overall charge on the ion. Give it a second. Good.
But it didn't have an overall charge.
Yeah, it does. -1. Okay, solving for iodine, we get +1. Good? Does that make sense? Lyric, do you have the worksheet in front of you?
Yeah.
Okay, so it is there. It's kind of hard to see, but it is there. We repeat that for the last iodate ion. So iodine plus 3 oxygen has to equal what? -1. Okay? Lyric, you're on the spot.
Let me catch up. Let me catch up. Okay, that would be 5.
Positive or negative? Okay, make sure we say plus or minus 5 just to make sure we're identifying the sign. Because if you write just 5 on a test, I know I'm taking off the point. I'm betting your grader might take it off too. Okay? I would hope your grader for the test takes it off because you know better. Okay. Now, we identify our half reactions. We're going to identify them this time using oxidation numbers so we get used to seeing them and understanding we identify based off of changes. Is oxygen changing? No, oxygen doesn't usually change unless it's existing on its own. So, what is changing? I think it's rhenium and then iodine. So those are our 2 half reactions. Which one's being reduced? So which one has its charge being reduced? No, if you just look at the numbers, its oxidation number is being reduced. So reduction, because you're adding electrons, reducing its oxidation number, it becomes more negative. So there's another way to make things a little bit easier for you. Then the other one should be oxidation or losing electrons. So here's our oxidation half reaction.
Oxidation is losing electrons.
Yes, reduction is gaining. Because you gain electrons, your oxidation number should be reduced. And in your mind, you think that becomes more negative, right? In your math class. That's because you're adding electrons. Okay, writing our reactions, ReO4 becomes Re, and then IO1 minus becomes IO3, 1 minus. Good so far? Okay. First, starting by balancing non-hydrogen oxygen atoms. There aren't any. Next, we balance what? Oxygen. So doing the left-hand half reaction first. What are we going to add? For water, which side? Okay. Matthew and Sam are not allowed to talk anymore. Okay, everyone else, my quiet people, because it's the rest of you. The iodine half reaction. Which side are we adding water? The left. How many? Good. Questions? After adding water, what do you balance? Hydrogen. So we balance oxygen, then we balance the hydrogens. We balance hydrogen by adding what, Kayla? How do you balance hydrogens? What do you add? We're going to balance hydrogen now. What am I putting on the other side? I have 8 hydrogen. So what am I adding to the other side? Well, that works too. I have to add hydrogen to both sides. This one is 8 what hydrogens though? How am I representing the hydrogen? H plus, so hydrogen ions because it's acidic solution. Then I'm going to add hydrogen to this side. How many? Good. My last step before I get them ready to recombine is to do what? I balance atoms, I balance water, add electrons. So I balance atoms, I balance oxygen, I balance hydrogen. Now I balance charge with electrons. So looking at the left-hand half reaction, which side am I adding electrons to? The left. How many? 0 and positive 8. How do I get those to equal? Oh, no, it does. Does it? No, it has a 1 minus. There we go. So it is 7 electrons. Thank you, guys. I forgot to write that.
This is where it really confused me because 7, I like couldn't.
Yeah.
We'll get there. We'll get there. We'll get there. So, and it's going to be, this one is a big reaction, so it's okay. It is a big reaction. So now I have 8, a positive 8 plus negative 1, maybe plus negative 7. Maybe. Where did the 7 go? Has to equal 0. Does that equal 0? Yes, so that's good. Now we'll do the charge on the other side. You good, Brendan? Okay. Charge on the other side. What? Where am I adding electrons? Negative 1 has to equal negative 1 plus 4 positives. Give it a second. There it goes. So this is positive 3 here. How many electrons do I need? Say what?
Wait, wouldn't it be like 4?
4.
Oh.
So when I add the 4 negative 1 charges, I end up with negative 1 overall. Because these two cancel out.
Pause. Yeah, this is where I got lost.
What's up?
This is what I got.
Just pause. I need a second.
Wait, so there's negative 1 charge for that, and then there's a positive 4.
So I'm back at this. Ready? I'm back here. I know which side do I need to add electrons to? Products or reactants? Product side, right? I add it to the more positive side, but I don't know how many I have or need. So plus X number of electrons or negative 1 charges, right? Let me erase that and write. Good. Solving for X. How many electrons? So, so then X has to equal 4. So I'm going to sub that in up here. Maybe. We are restarting my laptop next. I'll record period 3 stuff too and post it for you guys, so don't sweat it. I mean, you can listen to this for like how bad of a hot mess it is during 5th, but good.
I don't understand how you got the 7 electrons on the first side. I understand how you got the 4 electrons on the...
It has to equal what overall charge on the product? What's the overall charge? 0. So I have a positive 8, 8 times positive 1, plus a negative 1, plus what to get 0? Some number of x times negative 1, solving for it, positive 8 minus x, no, not positive 8, positive 7, because I can do math, has to equal 0, so x has to be 7. Cool? That makes sense? It's early, don't feel bad. Okay, I heard that we got stuck on how do we figure out what to multiply by. Yep, least common multiple. Yep, it's a big number. So when they aren't easy to make the same. So I'm going to multiply this one by 4 and this one by 7. And I'm just going to be lazy and stack them as I go. So 32H plus 4ReO 4 1 minus plus 28 electrons. Give my computer a second to catch up. Oh boy, where did it go? Maybe not. That's not 7.
Doesn't matter what order you write it in?
Nope. As long as it's on the correct side. 4 Re plus 16 H2O. Now we do the other one. 14 H2O plus 7 IO 1 minus yields 7 IO 3 1 minus plus 28. There we go. I got it right. Check my math, please. Check my math. Make sure I wrote it all right. Notice that by multiplying by these coefficients, it cancels out. Okay? Like, they stay balanced, but it cancels out. What's up, girl? You okay? I recorded it. This one's a hot mess, so it'll be a giggle fest. I'll record tomorrow's as well. Okay, so these, whoops, no erase. Cancel out your electrons first, because that's easy. What else can you cancel or reduce? Hydrogens. So 32 and 28, this one goes away, and we keep how many? What else? H2O, 16 to 14. 14 goes away, I'm left with 2. I've simplified, now I add them together. 4H plus 4 ReO 4 1 minus plus 7. Nope. Four Re plus 2H2O plus 7IO 3 1 minus. Maybe it'll go. No, it won't. I think my computer needs to restart. Even my computer's done with this.
Okay, this actually makes sense now.
Yeah.
Better?
Yeah.
Okay, we have 20 minutes to do a basic medium. Okay, we good? Any questions or confusions on this one? and we'll readdress some of the stuff we've been going over. So, like, if you just want to absorb or if you want to take notes, you can pull out your notebook and follow along. Okay. No, I'm not going to do one of the practice problems because this one in the textbook looks kind of hard. So this is 19.3 practice problem on page 893. So you can see like where I'm getting stuff from. So balancing in basic solution. I'm going to do the practice problem they give you to practice on your own. You can go to page 892 and look at the walkthrough that they do right before for a different problem. Okay. So here we go. ClO minus plus CrOH4. Nope, 4's on the wrong side. 1 minus. I'm going to put the 1's in.
What is this called? Like a medium?
Basic, medium, or basic solution. CrO4 2 minus plus chloride. Good? Okay. Chloride, Cl 1 minus, sorry. I like have allergies and it's all draining. It's glorious and not. It's gross. Okay, ready? Okay, assign your oxidation numbers. Which ones are super easy right now? Cl on this side, right? Because that would be a -1. All monatomic ions get their charge as an oxidation number. What else is easy?
Wait, I thought they got 0.
No, that's an ion. Elemental gets 0. This has a charge on it, so it gets its charge. Oxygen is easy. What's another easy one? Hydrogen. So the oxygens are what? -2. -2. +1 for hydrogen. -2. Good so far? Okay. So elementals get 0. Monatomic ions get their charge. We assign fluorine that's not there, a -1. We assign hydrogen a +1. We assign oxygen a -2 in compounds. Good? Then we use some algebra to figure out the rest. Our first chlorine has to be what? +1, because Cl plus a -2 has to equal -1. Chromium in the next problem. That one's a little more funky. Using our algebra, so Cr plus 4 times -2 plus 1, maybe it'll show up, has to equal what? -1. Somebody besides Sam, let's do the math. Or Matthew. Are you confused, Kayla? Processing. I'm going fast because we've got 15 minutes. Solving for chromium. Cr plus 4 times -1 is -1. Cr minus 4 equals -1. Cr then has to equal +3. Good. You do not have to show this work because it's implied with algebra skills that are assumed. Come on, go away. You won't be docked ever for showing extra work. Okay? As long as it's correct work. Now on the other side, solving for chromium. It is +6. Anybody need me to show that work? Anna, sweetie, you good? Did you oversleep?
No, I went to the dentist.
Oh, okay.
-2.
Wednesday. You won't be in here. Yeah. ASVAB for juniors. Wednesday.
What is that test?
Oh, so maybe.
It's the military placement test. Like career placement. It's military and career placement. I'm sorry. So we'll be in here for like I don't know how long, just enough to check in and take roll, and then we report to testing spots.
I think this is.
Is it positive 4?
It might be your testing spot. I have to move. What?
Positive 6?
+6. Do you need me to go over it, sweetie?
I think I looked up there and seen positive 6, so I used that instead of.
Oh.
Yeah.
Do we see how we get +6? Okay. So now we can identify our half reactions. Which two are changing? Chlorine is, and chromium. Even if it's a sign change, that's a difference of 2 electrons. Which one is being oxidized? Which one's being reduced? So the reduction one is easier. Which one has its charge being reduced? Chlorine. So this is reduction. Just to keep reviewing, which one has my charge being or my element being oxidized? Electrons removed. Chromium. Thus, we have redox reaction.
Yeah. Is that because you went from +3 to +6?
Yes, because it loses electrons. I take electrons or I take negative charges. Taking, subtracting negatives is positive. That's why I told you identify the reduction one first, right? Because reducing your charge is easier to comprehend. And reduction is always partnered with oxidation. So if chlorine is being reduced, the other one has to be oxidized.
I think what's getting to me is like when you say reduction, I'm thinking like you're losing electrons, so it's getting more negative.
Your charge is being reduced, or your oxidation state is being reduced. Think of it that way for reduction, because you're adding electrons. You're adding negatives to reduce your oxidation state. Got it? Okay, so writing our half reaction, ClO1 minus becomes Cl1 minus. My other half reaction is the chromium hydroxide, whatever fart that is, compound, to the chromate. No, that is chromate. Ion. Good? Okay, another one where the atoms are already balanced, right? Besides hydrogen and oxygen. So we don't have to do that one. Next, we balance oxygen with what? H2O. There is one additional step that you have to simplify extra. Okay? So, ready? So we add, it's pretty much the same until right after we balance our hydrogens. So, balance oxygen, what's up? You need Miss Fanning?
Yeah,
Balance oxygen with water. So I'm going to add a water here. And then on this side, I have 4 and 4. Do I need to balance it? No. Okay. Now we balance proton or hydrogen with hydrogen ions. Same steps. So I'm going to add 2H plus here for the 2 hydrogens I have here. And then I have 4 hydrogens here. So I'm going to add, 4H plus here. This is acidic though. How do you cancel out acid? With the same number of base. What is base? Thinking back to our titration question, H plus is acid. What is base? It makes a salt. So if water is HOH and it's amphoteric, meaning it acts as both an acid and a base, this is its acid part. What's its base part? So this is the OH. I cancel out my H by adding OH. So I have to make this basic. It's already balanced with its atoms. So if I'm adding OH, how many do I need on, well, let's do this, the left side. On the left side, how many OH do I need to cancel out my H? How many H's do I have? 2. So how many OHs do I need? 2. I add it to both sides so it stays balanced.
But if you already have the hydrogens and the oxygens balanced, then why do you need to add?
Basic solution. So you can react under acidic conditions or basic conditions. Some reactions don't go under acidic conditions, so you have to make it basic.
So the acidic ones have been the examples before?
Yes. Now the difference is base. So when I add 2OH here, I have 2 hydrogen ions plus 2 hydroxide ions. What does that make? 2 H's plus 2 OH's makes what? How many water? 2 waters. So this I can simplify to 2 water. It is extra. Okay. I'm not going to simplify any more from there because then I'm erasing a whole bunch of stuff, but you could simplify some more, can't you? Or we can simplify more in this left-hand reaction. What can you simplify? I can get rid of this one, and this becomes 1. See the other half now? Ready for the next? Do this. We'll do the next half. Okay, other half. I have 4 hydrogen ions. How do I cancel out hydrogen ion? By adding OH. So I'm going to add 4 OH to both sides. This makes it basic. Good so far? OH plus H makes what? Water. How many waters are we making then? So I'm going to erase this, maybe, and write 4H2O. On mine, because I did all of mine in pen, I think I cancel it out and write water next to it or something. Or I circle it and write the total water. And this is my barrier between the two. Okay. Good. So making water comes from adding that hydroxide. That's the extra step. You can wait and simplify. So how I had, like I canceled out this and I have a 2 here. Dang it. Right, so I had this 2 here. I can simplify my waters in the half reaction because I have it on both sides. Does that make sense? Just like in algebra, I can simplify that, and this becomes 1. Cool? So that's the extra step, is after adding the H+, because that's how I always balance hydrogens. Basic solution is the hardest one, because you have one more step that gets funky. Okay? But since you're adding charged particles, you have to do this before you add electrons. Got it?
So is it okay if I
Left the water and balanced and got rid of it at the end? Yes. As long as you account for it and take care of it by the end, you're good. It doesn't matter where, because it's additive properties. It's algebra. It doesn't matter where you simplify, as long as you do at some point between now and the end. Okay? Our last step is to balance electrons, or balance charge with electrons. So I have a -1 on this side, and it has to be equal to -1 plus 2 -1s, because this is 0. And I technically canceled it out. So this is -3. Which side needs electrons? The what? I'm going to add 2 electrons here. So that's adding 2 -1 charges. Give it a sec. There we go. So now it's -3 on both sides. Good? Remember, you're adding negative charges, so you got to figure out which side needs to be, like, dropped down. More negative. Okay, on the right-hand reaction, we have 4 -1s plus a -1 has to equal -2. Which side needs it? Hint, it's the opposite side of the left reaction. Products, how many? How many? Is it? Oh, it is. Cool? -5. So -4 plus a -1 is -5. And then -2 needs 3 more negatives. Good there, Kayla? Okay. Ready? Now we're ready to combine, but what do we need to do? Yep, so we're going to...
Did you get the 4 negatives from the 40H?
Yes. So I'm going to multiply this one by 3 and this one by 2. I'm going to rewrite them. Hopefully. 3H2O plus 3ClO minus plus 6 electrons yields 3 chlorides plus 6 hydroxides. Okay, doing the second equation, 8 hydroxides plus 2 chromium, whatever what this ligand is, yields 2 chromates plus 8 waters, plus 6 electrons. Did I get all the math right? All my charges are assigned. Oh, thank God. Now we simplify. Electrons are easy. What else can be reduced? OHs. So 6 and the 8 becomes 2. What else? Water. This goes away and the 8 becomes 5. Anything else? Now we just write it out. Oh boy. 2 hydroxides. Eeny, meeny, miny, mo. I usually pick and just start furthest most left and then go towards the right. As long as you write everything, because it's additive properties, right? It doesn't matter which order, as long as they're there. Okay, studying for the AP test.